As we continue the second set of chapter 9 for these work problems, we're going to really move into this Hess's law. This is now enthalpy of reaction using two different techniques. There's really three methods of using Hess's law. One would be that we're going to say, okay, one way I can get there. It's all about being path independent. If I can find a path that's the same, ends, it starts and ends at the same place of the reaction of interest, and I know about the enthalpy of that path, I can then say something about the enthalpy of the reaction. I can at least make a good theoretical calculation of it. So one way we can do it is we can use these enthalpies of formation, standard enthalpy of formation. And I would take it for the products and the reactants because this is how much energy it is to form them. And I want to unform, to form the products, I would use the positive value. But over here, I would have to basically unform the reactants, get them down to standard state elements, then put them together to make the products. So since this I'm unforming, I would use the negative sign. We usually put it at the second term. So this is like taking assembled Lego structure, pulling it all apart down to individual Legos or whatever the standard state elements are, the base pieces, and then reconstructing it into something else with all the same Legos. That would be the products. Another way I can do it is that I can use the bond energies of which bonds are being broken and how many of them there are. That would require energy, so it's a positive value. And then which bonds are being formed. I know bond formation releases energy, so I would subtract that because I'm getting that energy back. And that would be another way to predict the enthalpy reaction. The third way is if I had a series of stepwise reactions that I knew the enthalpy of, that I could adjust in some situation, I could do them stepwise. I might have to do them reversed or whatever. I can now add all the enthalpies of the steps to a total enthalpy of the overall reaction. So we're going to do some of these first and second types. So I'm going to be using these two equations. Again, which one do you use? Well, what do you have available to you? If you have the enthalpies of formation, use that. If it's talking about bond energies or it gives you Lewis structures or it's giving you things like that, so then we can use the bond energies. It's basically what is it hinting at in the question and what do you have available to you that would work? All right, so first let's talk about for this the standard heats of formation, enthalpies of formation. It is defined as the energy to form 1 mole of substance from its standard state elements. And again, this is usually already tabulated for us, so I might be able to find these values, but it's important to be able to recognize some of these things. So sometimes I'm like, yeah, what are they actually talking about? What would be the reaction associated with forming this substance, 1 mole of the substance from its standard state elements? So I want to make 1 mole hot, water gas. So I'd have to think of what are the elements in it? Well, it has hydrogen and oxygen. So what are the standard states of those? Since hydrogen, they're both diatomic and they're both gases at room temperature. So we would say that the standard state element for hydrogen is H2 gas and the standard state element for oxygen would be O2 gas. But I now need to have a balanced reaction. So note that my balanced reaction is 2 hydrogen gas plus oxygen gas makes 2 moles of water. Well, let's say just 2 moles, 2 waters. We don't usually write the word moles in there, it's implied. 2 H2O gas. So now I have to reduce to just 1 mole, but leave it balanced. which means I'm going to divide all the coefficients. Which means I will end up with fractional coefficients. Hydrogen gas plus half a mole of oxygen gas. 1 mole of hydrogen gas plus half a mole of oxygen gas, making 1 mole of water in gas state, 1 mole of steam. Notice that you say you can't have fractional coefficients. But remember, I'm not doing this reaction. This isn't an actual reaction. I want to know the energy. So what would happen is this would be the reaction that occurs. And I would get some amount of energy. I'm like, yes, but that would be the energy of making 2 moles of water. And I want to take half of it to say, well, what would it be for just 1 water if I could make just 1 water at a time? So it doesn't matter. I'm not going to conduct this reaction. It is a theoretical number, and then we're talking about the energy. So that's why we're allowed to have fractional coefficients when we're talking about thermochemistry. You can't do it when we're actually doing real chemistry, though. Okay, so calculate the enthalpy of reaction for this reaction, and it gives me calcium phosphate plus sulfuric acid makes calcium sulfate plus phosphoric acid. So if this was provided nearby, notice given I have the enthalpies of formation, standard enthalpies of formation for all substances. I don't see any bond energies. I don't see any Lewis structures. These would be kind of complicated. We got polyatomics in here and have a lot of bonds being made and broken, maybe. So this is a little bit trickier in that maybe I don't use enthalpies of reaction. So I'm looking at what do I have available to me. Now, if I went to the table and I didn't have these enthalpies of formation, then maybe I'd say, well, let me see if I could do it with bond energies. Okay, we have the enthalpy of reaction is equal to the sum of enthalpies of, well, actually it's N, which would be my coefficient. So it's how many moles am I making, which is really my coefficient, times the standard enthalpy of formation for all products minus the sum of moles times enthalpy, standard enthalpy of formation for all reactants. So I kind of like to just do terms of N delta H F. So I know that this is 1, because that's the coefficient for calcium phosphate, and we find calcium phosphate is -4126. We'll assume these are all in kilojoules per mole, so I'm not going to write the units. And this would be 3 times let's see where I have them. Figure it out. Here we go. 3 times -814. And for this, it would be 3 times -1433. And this would be 2 times -1267. So this would be -4126 and -2442. And if I sum them, I get -6568 is the sum of the reactants. And over here, this is -4299 and -2534. And if I sum them, this is -6833 for my products. Again, my delta H is equal to, this should have been standard, is equal to the sum of the products. Sum of products minus the sum of reactants. So this will be -6833 minus a -6568. These are all in kilojoules per mole. So note that this ends up being positive because I have a double negative, and I end up with -265 kilojoules per mole. So they're not really particularly hard. I just have to be careful and tabulate it. I do like using this method of writing them directly beneath each one, adding up the total of the reactant side, adding up the total of the product side, and then go to the formula and do the products minus the reactants. All right, this is a similar problem. Ammonium perchlorate mixed with powdered aluminum mixed with powdered aluminum powers the space shuttle booster rockets. I have an equation. I'm given an enthalpy of reaction. Let's assume that's a 0. Given the following thermochemical data, what is the standard enthalpy of formation of NO? So no, it's asking about this thing. It wants the standard enthalpy of formation of this thing, and it gave me the ammonium, it gave me water, gas, it gave me aluminum oxide, it gave me ammonium chlorate, it gave me HCl. It didn't give me aluminum, and it didn't give me NO, but that's the thing it's asking for, but it did give me the total. So again, let's kind of organize it in this system. So we have 2 times, I'm going to do my N delta HF terms. 2 times ammonium chlorates is negative 290.6. By the way, this is negative 581.2. It didn't give me this. Remember, the enthalpy of formation for standard state elements, since I already am in standard state element, to make it from standard state elements, there is nothing that's happening. It's already there. So they're defined as, so based off of the definition, they're always 0. So this is going to be 2 times 0, which means this is 0. So summing the reactant side is pretty easy, negative 581.2 for the reactants. Now over here, I have one of the aluminum oxide. So that's going to be 1 times negative 1669.8, 2 times negative 92.3. This we're going to call 2x because this is what I want, is the enthalpy of formation. So I'm going to say 2x, and then this is 3 times negative 242.1. So this is not 669.8. This is negative 184.6, 2x, negative 726.3. And if I sum these, it's going to be negative 2580.7 plus 2x. Now remember, delta H equals the sum of the products. This is my product sum, minus my sum of reactants. But in this case, I have one more piece of information. I know that this is negative 907.7. And that's going to be equal to my sum of products, which is negative 2580.7 plus 2x, and then minus negative 581.2, which is going to be a positive. This, if I collect my like terms, I end up with negative 907.7 equals so I'm just going to subtract all these from this side. So let's do plus 2580.7 and minus 581.2. So on this side, I'll leave this plus 2580.7 minus 581.2. This will leave alone. And I get, this would be 2x. So this is 1091.8 kilojoules per mole equals 2x. So I divide both sides by 2, and I get that x, which is the delta HF of NO, is equal to 545.9 kilojoules per mole. So a little bit more work, but it's just really more algebra. This concept is exactly the same. All right, now let's look at some other types. Let's look at, this even tells me using an appropriate bond energy. So since it's talking about bond energies, I'm going to use the bonds energies situation. So this is the sum of the number of bonds times, and this is the number of moles of bonds. We'll do it in terms of moles, but it's the number of them, quantity times the bond dissociation energy for the bonds broken. And then I'm going to do the number times the bond association for all the bonds broken. And then I'm summing up all the ones broken. Oops, made. Now I have to look back at the original page and see if I had a typo there. And I would sum all these up. And then last step, I would take the sum of the broken minus the sum of the made. All right, so notice in this case, what are we breaking? When I'm looking at this, I start with HH, H2, and Cl2, but I'm writing them out in their bonded state, like a Lewis structure type, so I can see the bonds. And then I'm making two HCl's. So I'm going to have to break this bond and break that bond. And then I'm going to swap them and make these bonds, but I'm going to do it 2 times because I have 2 hydrogens and 2 chlorines, so I'll make 2 of these. So the bonds that are broken have 1 HH and 1 Cl, and the ones that are made is I'll have 2 HCl because there's 2 of them, so I multiply by 2. But within the product, there's only 1 HCl bond. All right, so we end up with, this would be 436 and 243 for a total of 679. And over here, and I'm just using these values from the table. 2 HCl's would be 2 times 431. So this would be 862, and delta H equals the sum of broken minus the sum of made. So 679 minus 862. Note that I get back more energy than I put in to break them. I get back more by making the bonds. So overall, this will be a negative 183 kilojoules per mole. So it would be exothermic. It didn't ask me that, but when I'm done, one of the values of getting an enthalpy of reaction is telling me, is this an endothermic or exothermic process? All right, let's look at another one with a little bit more detail, more bonds, so that we kind of have to look at it a little bit more. All right, this is the same idea. It's telling me use the appropriate bond energies, but now it's looking at the following reaction of ethanol plus oxygen forming CO2 and H2O. So this is the combustion of ethanol. So I've shown you the Lewis structures so that we can kind of really see the bonds that are being made and the bonds that are being broken. See if I have this. Get it. My little cheat sheet. Here we go. Okay, so note that we have a bunch of CH bonds. So I have CH bonds. I have CC bond. I have CO bond right here. And I have OH bond. Technically the O, well, we'll do it anyways just because it's easier. And then I also have an O double bond, O bond here. So let's count up how many I have. A highlighter. So note that I have 1, 2, 3, 4, 5 of these. So we have 5 CH bonds. I can see that there's just 1 CC bond. So I've got that one. And I have 1 CO bond. I've done that one. And I have 1 OH bond. I've done that one. Now, really, there's 3 of these. So it's 3 coefficient times 1. There's only 1 within it, but it's 3 of them because I have 3 here, whereas I only had 1 of these. And then on the ones being made, I have within the CO2, note that I have 2 C double bond O bonds, but then there's 2 of them. And then in this product, I have a coefficient of 3 times, again, I have 2 OH bonds. All right, let's write down what we have. So this is 5 times 413, 370, 385, 497, and 3 times 498. And if I add all those up, that should be 4811 kilojoules per mole, sum of broken. And up here, note that 2 times 2, this is going to be a total of 4 times the C double bond O's. Watch out, right? When I go to look at this, this says it is 799 in CO2. So for this is the only example where I have to kind of be careful. Generally, I just need to know the bond. But the bond energy is significantly different for CO2. So that's 4 times 799. And then 6 times my OH, which is 497. Now, maybe you go back and you realize, look, this bond never really got broken. This bond gets broken, and then this one, I just need to add another hydrogen. One of these bonds, once the hydrogen comes off, could bond over there. So I really had one that stayed intact and never broke. So notice that I have 1 over here being made and 1 being broken and 6 being made, but really this one never got broken. It's just 5 being made, but it works out because I'll just basically, the one of these cancels out. It's fine. This is a little bit complicated to see all that because there's so many bonds being broken and made. This would total up to 6178 kilojoules per mole, sum of the made bonds. So now delta H equals the broken minus the made. So 4811 minus 6178 for a total of negative 1367 kilojoules per mole. So these combustion reactions they're pretty darn exothermic, which makes sense, right? This is burning ethanol. This is a fuel. So I'm getting a good bit of negative, meaning it's exothermic, and I'm getting a relatively high number because of so many bonds. I have to break a lot of bonds, but I'm making a whole lot of bonds and getting a lot of energy back. So hopefully this helps you figure out how to do all the math and maybe get some conceptual stuff on this chapter. It is a lot. There's a lot of signs and a lot of math, but you can do this.